Good evening students. Today we are going to discuss on Maxwell's equation. Before starting the derivation, we will look into the Faraday statement. What Faraday stated? He stated that electric field can be produced by the changing magnetic field, whereas Maxwell's concept describes about magnetic field can be produced by changing electric field. So these two are electromagnetic concepts, and Maxwell's equation derived four set of electromagnetic equations based on these laws: Gauss law, Faraday's law and Ampere's law. Based on the Stokes or divergence theorem, every Maxwell equations has been formulated. Now let us look into the Maxwell's equation from Ampere's law. Ampere's law, everyone knew that. Ampere stated that the total magnetic field over a closed path is equal to the current enclosed by that path. That has been mathematically equated as integral h dot dl is equal to I, where I is the current enclosed by the path. In terms of current density, we can represent this as integral j dot ds. We are talking about current. The current is a combination of both the conduction current and the displacement current. Current that flows through a resistive element is termed as conduction current, and through a capacitive element is termed as displacement current, which is IC and ID respectively. First, we have to derive for conduction current, and then we can go for displacement current density. So, conduction current, as we already mentioned, the current through the resistive element is conduction current. IC is equal to V by R. Based on Ohm's law, V is equal to IR. IC is nothing but V by R. And as per the formula we know, resistance R is equal to rho L by A. Resistivity of the particular material, length of the conductor and the area of the conductor, which in turn can be written as in terms of conductivity. Inverse of conductivity is resistivity. Therefore, L is which is equal to L by conductivity into A. Therefore, IC is equal to V. Substitute for R, which has been given here, L by sigma A. Therefore, sigma A goes to the numerator and the L is in the denominator. And we have already discussed that V is equal to voltage developed is equal to field into the distance or length, which is equal to V is equal to E dot L. Substitute for V here in IC equation, E dot L sigma A divided by L. Can be cancelled, and which is equal to E sigma A. And in terms of current density, means then we have to define the current per unit area. Therefore, IC by A, which is equal to sigma E. IC by A is the conduction current density, JC, equal to sigma into A. This is the conduction current density. When coming to the displacement current density, displacement current density is nothing but the current that flows through a capacitive element. Therefore, it is termed as ID. Capacitive element means we have to consider capacitor, whereas C is equal to V by Q or Q is equal to CV. The current through a capacitive element is equal to dQ by dt. The rate of change of charge present in the capacitor is termed as the current. Therefore, ID is equal to, substitute for Q here, it is C dV by dt. And we know the capacitance of a parallel plate capacitor, which is equal to epsilon A by D. Epsilon is the permittivity of the material, A is the area of the plates, and D is the distance between the plates. So substitute for C here, and ID is equal to epsilon A by D and dV by dt. And substitute for V also, epsilon A by D, and in terms of d gets cancelled, V is equal to E dot L or E dot D. d gets cancelled, dE by dt, and therefore ID becomes epsilon A dE by dt. In terms of current density, means we have to divide the total current with respect to the area. Therefore, ID by A, which is equal to epsilon dE by dt. And we know that epsilon E is nothing but D. Therefore, replace this term with dou D by dt, which is nothing but displacement current density JD. So, these two currents forms the total current for the Maxwell's equation. And we have discussed about Ampere's law, that is the total current enclosed in the closed path or the magnetic field through a closed path is equal to the current enclosed. In terms of current density, we can write it as integral S J dot ds. So, J is nothing but the total current is nothing but the sum of conduction current and displacement current. Even writing in terms of current density, it's also the same. conduction current density and displacement current density. Integral is Jc plus Jb into ds. So substituting for Jc, what we have found over there, sigma into E, and similarly for Jb, dou d by dou t, which is nothing but integral h dot dl is equal to surface integral. We can write sigma E in terms of J also. Both the equation are correct. Any terms is preferable. J plus dou d by dou t into ds. So this is the integral form of Maxwell's equation. Coming to the differential form, wherever we have to identify differential form of equation, we can apply Stokes theorem. Stokes theorem relates line integral and surface integral. Integral h dot dl is equal to del cross h ds. Comparing those two equations, that is integral del cross h ds is equal to right side of that equation integral j plus dou d by dou t into ds. Then the surface integral can be ruled off, and the remaining term del cross h is equal to j plus dou d by dou t. So or else we can write del cross h is equal to sigma e plus dou d by dou t. This is the Maxwell's equation which has been derived from Ampere's law.